So before we even begin to talk about calculus concepts, we're going to start with a preview. So what is the purpose of what we're doing? Why do we need to go through all this stuff? And what kind of questions are we going to solve? So calculus is really talking about mathematics of change, whether it's velocities, accelerations, slopes, areas, curvatures, the list goes on and on and on. But really we use calculus to model and solve real life problems. So you learned about some stuff in pre-calc where you were able to calculate distances, you were able to calculate like projectile motion with parabolas. So you may have seen some velocity and distance problems, but we're going to try to make it much more dynamic in calculus. So to give you kind of just a feel, we're going to look at pre-calc versus calculus. So in pre-calc, you were able to find the object of So in pre-calc, if you had an object traveling at a constant velocity, you were able to calculate the distance. If I walked at 10 miles per hour for 2 hours, I walked 20 miles. So my distance was just my velocity times time. But now what if I'm running and I slow down and I speed up and I've got an object that's accelerating? What would then be my distance? Because over certain intervals, I'm traveling a certain speed and it's constantly changing. So how do I go about calculating that? Now, what about the slope of a line? We dealt with that before. If I have 2 points on this line, I need to know what that change in x is, which I'll call delta x, and I need to know that change in y. So my slope would then be my change in y over my change in x. Now what about a curve? What if I have a function that does something a little bit funky? And I want to know at this specific point what my slope is. So I need to know the line that passes through this, but I don't exactly know what that change in y and change in x are because I no longer have another point on this curve. So this would be my change in x, which we're going to call dx, and my change in y is dy. How do I figure out what these two are? Okay. What about if I want to find the area under a rectangle or another geometric shape? I can use that with basic formulas. So if I have a nice function, my x values, my y values, and maybe my y value is always equal to 2, no matter what we do. If I want to find the area under my curve from, say, 3 to 6, definitely not drawn to scale, but that's okay. This is just a rectangle, and I know how to find that area. So this height would be 2. The width of this is 3. My area is then 3 times 2, or 6. But what if I give you an arbitrary curve? I go from some value A to some value B, and maybe I'm looking at like a parabola type shape. So here's my function. And I want to know what the area under this curve is going to be. But I no longer have a nice geometric shape going on because I've got that curve on the top. It's not quite a circle. It's got a whole bunch of stuff going on. So how do I figure out what this area is equal to? Okay. So the one trap I don't want you to fall in is you're used to memorizing formulas. Calculus isn't quite about that. You don't want to try to do rote memorization. You don't want to try to sit there and just blind feed that formula. Of course, there's going to be formulas to remember, but you really need to approach a subject with exploration, logical reasoning, and realistic interpretations. So you have to go and know what's going on in that process. What am I really doing and why am I doing this? To be able to really gain a good understanding of this subject. So to be able to answer a lot of these questions, we're going to take the ideas we know from pre-calc and extend it to get these more dynamic problems. So we're going to start with these pre-calc concepts. We're going to apply what's known as a limit process, which is what our first chapter is going to be completely about. And that's going to give us our calculus concepts. So we really have two fundamental ones we're going to be learning about. We've got a tangent problem and we have an area problem. So we're going to talk about what each of these are so you understand what goal we're ultimately trying to get. So we'll begin with the tangent problem because that's where we're going to start first. The word tangent derives from the Latin word tangens, which means touching. So a tangent line to a curve is a line that just touches the curve. So if I give you some examples, maybe we've got a circle and maybe we've got like a cubic function of some sort. If I have these 2 points here, my tangent line is going to just touch the curve and go away. 2 other points, I touch the curve and I go away. Okay. If I continued this tangent line, it would touch in another spot, but nearby this particular point, it's only one spot that touches. So this line is a lot harder to find because I don't know the slope. I know a point, but how do I find the slope of this? Well, what we're going to do is talk about secant lines. So the word secant derives from the Latin word secans, which means to cut. So a secant line is a line that intersects or cuts a curve more than once. So if I go ahead and look at these same 2 examples, if I find the secant line between those 2 points, I just connect the 2. Okay? I connect those 2. So ultimately, the secant line we can calculate pretty easily. We've got 2 points on the curve. We find the slope by looking at the difference in y values over the difference in x values. I've got my slope, I've got a point. We write the equation of the line. But that tangent line is a lot more complicated because we only have a single point. But the nice thing is there is a connection between these 2. And this is something, the secant line, you're used to finding without having called it a secant line. So let's take a look at the relationship between these 2. In all of these instances, I've got this tangent line at point P. I don't know the slope of that tangent line, I just know a point it passes through. So if I pick a point pretty far away, we'll call this Q from P, I could find the line between Q and P using my x and y values and finding the slope. But this secant line would be such a poor approximation. This one's going down, this one's going up. Definitely not accurate at all. If I move Q closer to point P, and I find the secant line between those 2, this one's much better. If I move even closer to point P, and I find the secant line, I'm near identical to that tangent line. So ultimately, as Q approaches P, the secant line starts to look like the tangent line. So this is what I need to do. I need to let Q get closer and closer to P, and that's what this limiting process is going to allow us to do. So let's try an example. Let's consider the function f of x equals 1/2 x squared and the point 2, 2 on the graph of f. We're going to graph our function, we're going to graph the tangent line at 2, 2, and we're going to graph 2 secant lines when x is equal to 3 and x is equal to 2.5. So first thing I'm going to do is I'm going to graph this function. It is just a parabola. If I plug in 0, it goes through 0. If I plug in 2, it tells me it goes through 2. But if you plugged it in, it'd be 1/2 times 2 squared. 1/2 times 4 is 2. So my parabola looks something like this. So this is f of x equals 1/2 x squared. Okay. Now, if I want the tangent line here at this point, I'll call P, it's going to pass through this point and just touch. So it's not going to be precise, but that's okay. This is what my tangent line will roughly look like. Going to have human error in these things. Okay. Now I need to find these two secant lines. And the first one I'm going to call Q1. This is when we're going to plug in x is 3. So I need to find what my y value is when I plug in 3. So that would be 3. If I plug 3 into the function, that's 1/2 times 3 squared. It's 1/2 times 9. That would give us 4.5. So when x is equal to 3, my y is equal to 4.5, which is roughly around here. So again, if I find that secant line, it's not terrible, but not super precise. If we look at the next point, when I plug in 2.5, we need to see what the y value would be here. So I plug that into the function. That's 2.5, 1/2 times 2.5 squared. And if you plug that into a calculator, this would be 2.5, 3.125. So when x is equal to 2.5, our y is right around here, and that's our point Q2. Connecting those two gives us a secant line that's much closer to the real tangent line. Okay. Now we want to find the slope of each of these. So I'm going to first look at the slope connecting P1 or P and Q1. So that would be looking at the difference in y values over the difference in x values. So I'll call this slope M1 just to keep with that same notation. My y values are 4.5 and 2. My x values are 3 and 2. So this is 2.5 over 1. The slope of this secant line is 2.5. Okay. Now if we look at our next one, if I look at the difference in these y values over the difference in x values, that will give us the slope between P and the point Q2, which I will call M2. My y values are 3.125 and 2, and 2.5 and 2. So this gives us 1.125 divided by 0.5, which is 2.25. So we want to use the results of this part to approximate the slope of the tangent line. And we want to ask ourselves, how could we improve this approximation? Okay. So as we picked a point closer, 3 is a lot further from 2 than 2.5 is. My slope went down from 2.5 to 2.25. I'd imagine if I pick something even closer, it's going to get smaller and smaller. As you see, it's going to drop down. It starts out steep, gets lower. So I would say probably the slope of the tangent line is 2, since those x values are getting closer to 2. But really, we could improve that approximation by picking something even closer. 2.01 is way closer to 2 than 2.5 or 3. Same thing, 1.99. It's on the other side, but that's really close to 2. So we could find the slopes of those secant lines to get a better approximation. Okay. All right, so our last problem is our area problem that we want to discuss. We want to figure out, if I give you an arbitrary function, I want to find the area between A and B. So here is my graph of my arbitrary function. I want to find the area under this curve from A to B. So our goal is to figure out, with this funky shape, and definitely not a nice geometric formula that I know how to find, the area of, how I can go about using these function values and using my knowledge from pre-calculus to get the area under this curve. Okay. So first thing I'm going to do is I want to use this concept way back up here. I know how to find the area of a rectangle. Let's use that to approximate area here. I'm going to cut this into two pieces, preferably equal length. I can find this length. I can find this length because I know I'm finding the area between 3 and 4, 5 and 7, whatever it may be. And I can use these endpoints and those function values to find the height of my rectangles. So I can go ahead and use rectangles as my approximation. So I can find the area of this rectangle using basic geometry and our function values, and add to it the area of this other rectangle. Okay. So in this instance, we're using two rectangles to approximate the area. Okay. So I would add those up. But now maybe I decide to bump it up, because if you notice, there's a nice gap between these. Let's do more rectangles. We've got two, let's double it and cut these in half again. So now I'm going to have equal width on the bottom, and I've got all of these heights of these rectangles using my function itself. So I would add up the area of these 4 rectangles to give me an even better approximation to my area under this curve. So you can see there is a lot less error going on than there is up here when I bump up and use 4 rectangles. Okay. So the more rectangles, the better our approximation ultimately becomes. So this is going to be where we kind of end the semester. It's our last chapter. So we'll see how these are closely related, but that won't be for quite a while. So we're going to spend a lot more time working with this tangent problem, which is our process called differentiation. And that will lead into this area problem. But all of this, we wanted to find this kind of stuff. This is what led to the birth of calculus itself. So we wanted these real life examples to solve, and we needed to come up with this foundation based on our prior knowledge. So let's do one more example. We're going to consider the function y equals x squared. And suppose we want to find the area between 0 and 2, first using one rectangle, and then using 2 rectangles, okay, based on these figures below. So we're dealing with y equals x squared. This point here would be the point 2, 4. So if I plug in 2, the y value is 2 squared, or 4. In this first figure, you can see it's not going to be a really good approximation because this is completely overestimating my actual area. But I can go ahead and use rectangles. This bottom is 2. The height of this rectangle is 4. So my area is approximately 2 times 4, or 8. Okay. If I go ahead and double the amount of rectangles, this point here would be 1, 1. Now, my width is 1 and my height is 1 for this first rectangle. My width is still 1 here, and my height is 4 for the second rectangle. So if I want this area, I go ahead and add these 2 up. The first one is 1 by 1. The second one is 1 by 4. So that's 1 plus 4. My area is roughly 5, which is still an over approximation because I've got a lot of gaps here. So if I went to 4 rectangles, 5 rectangles, 100 rectangles, I would get an even better approximation. So ultimately, we're going to learn what happens if I let the number of rectangles approach infinity. And that's going to help us find this area under the curve. Okay? So hopefully this gives you a nice little taste as to what we're going to be doing this semester. So we are going to start with the limiting process in the very next section, and kind of expand on that to be able to start with this tangent problem. And then that tangent problem, once we've learned how to master that foundation, it's going to help us actually solve this area problem in the near future.